So thank you for showing up for this session. And I'm here to talk about practical security foundations, which is interesting because I'm going to give you a whole session about security and encryption, and I'm going to try to doing that with zero math. The whole idea is that security is a relatively complicated topic, and the moment that people start talking about it, they throw words like P and Q and RSA and 2048-bit security and a bunch of other stuff. And at the end of the day, developers just want to be able to say, tell me what to write. Tell me what I need to do in order to make a secure system. So let's talk about what is actually security. And security, from my perspective, is basically just attacks. It adds zero functionality to the system. It actually takes functionality from the system, make things harder for me. But at the same time, this is a hard requirement. If I'm building a system with no security, then people can steal my data, people can see other people's private data, and a whole bunch of other stuff like that. Unpleasant. And it's really sad when you realize that the rate of unsecure system is so big and so commonplace that this is what it is almost different. If you're familiar with anything about security, you can go to shodan.io. This is a search engine that scans IPv4. It enumerates the entire IPv4 space, and for each potential server, it checks what ports are open, what is available, stuff like that. And what we realized is that you can go within the space of a few minutes to visit in the browser, to find a vulnerable server that has a system open with no security whatsoever, and you're deep in the guts of private enterprises. And this is insane. And when this happens, then the damages are incalculable. Now, sometimes, like the recent Uber attack, this was social engineering that allows someone to bypass a multi-factor authentication, jump into the internet, and start spreading from there. I'm not going to be talking about that. I'm going to be talking about what are the sort of things that you need to do to at least pass muster, to at least be able to say my application was built properly. So let's talk about this. One of the easiest way to talk about security, one of the biggest problem with talking about security is that proper security is not visible. If a door is broken, it's very obvious. If something is insecure, you don't see that. If something is properly secure, you would generally not see that. Now, I give the example here of the airport. If there is no security, you just go to the gate, you board the plane, you're happy. We have seen that the bad guys are also happy in this case. So what happened is that you have a security theater. You enter the airport, you stand in a long line, you wait, there's a whole bunch of limitations, and the bad guy is not actually limited by that. Okay, I can't get a bump on the plane. I can get a bump on the queue. Same exact end result. It's not in the air, it's on the ground. Big deal. Proper security in this case would be having the same experience as no security, but catching the bad guy. Now, typically, when we talk about software, there's 5 or 6 different elements that we have to deal with. And you can see that list here. And the theme that gets thrown around all the time is the notion of military-grade security. Well, we start with saying that military grade means the lowest bidder. The item that is just about sufficient to our requirements, and that was the cheapest that is possible. But in cryptography, in security in general, the actual attack surface that you have inside of a tank or inside of a server that is exposed to the internet, the server exposed to the internet is being attacked far more often. In general, you bring up a server on the public internet and it's going to be attacked within 5 minutes. Someone is going to probe it, see if they can attack that. The software on the tank, probably not connected to the outside world. At least I would hope so. So let's talk about some of the biggest challenges. Encrypting information, either in transit when we send messages to someone else, or encrypting information on disk, managing passwords, authenticating who am I talking to, certificates, which is a whole topic on its own, signing. So how do I know that this piece of data that you gave me actually came from where you tell me that it came? I can use digital signature for that. And finally, and what is probably the biggest issue, is how do you manage to secure the secrets, the keys to the kingdom, the encryption keys? So the first thing that you do, or you shouldn't do, is never roll your own encryption. The math isn't that hard. The issue is that there is a billion other things that you have to take into account when writing proper cryptographic code that you're probably completely unaware of. We're going to touch on some of them today, but in general, I want you to consider that if you're rolling your own encryption, the only reason why you should do that is to experience and to learn. And unless you have a PhD in cryptography, you probably aren't good enough to write production-worthy cryptographic code. And the reason I'm saying that is that the people who actually have PhD in cryptography, have built large-scale secure system, also tell you that. And they also have silly mistakes that would basically render the entire system completely absolute, completely insecure. So let's see some of that. How do we encrypt stuff? What does it mean to encrypt stuff? Well, it means that I have some sort of plain text. I do some operation on that, and I get secret text, encrypted text. And someone who has this encrypted text cannot tell me anything about what it means without having the key for the encryption. There is an easy way to do that. This is called the one-time pad. And this is mathematically proven to be secured. So if you have a one-time pad, this is something very simple. This is a list of bits, a set of bits which are chosen at random, and you basically XOR that with the text and you get some sort of encrypted text. And there is a mathematical proof that says that no one can hack that. No one can figure out what you said. Almost. Here are a few things that you have to take into account here. First of all, that pad must be random, true random, which means that you have to get it from some random source. And that actually turned out to be relatively non-trivial issue with most systems. For the most part, however, you don't actually care. You use urandom, you call this method or similar that promise to get you cryptographically secure random numbers, and that's it. Now, what are the limitations of one-time pad? Why aren't we always using the mathematically proven to be secure solution? Well, the answer to that is quite simple. It has limitations. So the pad size must be greater than or equal to the text size. And you can never, ever, ever, ever use that. This is what happens when you use a one-time pad. It's a catastrophic loss of all security guarantees. I'm not going to go into the why or the how of that. I mentioned no one in this talk. But the whole idea is that we need to have a way to encrypt data. And in order to do that, we need to have a one-time pad. And two entities need to have this one-time pad. I saw the text in one end, send it to the other side, then I XOR the encrypted with the pad and I get the plain text. And I'm happy. I got that. Except that along the way I did two things. I burned the one-time pad. I can never use it again, not even a single additional time. And now I have another problem. How do I send the next message? That's actually quite a big problem, because the size of the pad and the size of the text must be identical. Every time I send a message, I burn that pad. That sucks. So let's see what you can do. So we need something better than a one-time pad. What if we could use some sort of a seed and generate a seed of cryptographically a stream of cryptographically secure random bytes? Then we can XOR the message with this stream of random bytes, which are cryptographically secured. On the other side, I have the same seed. I can run the same operation. So I have the same output. And that's awesome, because now what I can do, now I have a way to generate a one-time pad. And I XOR that with a message, send it to the other side, generate the one-time pad, XOR that again, I'm good. But what happened with the next time? What happened when I want to do it again? Well, it's the same mathematical operation. I cannot reuse that. So, okay, great. Now, instead of having to send a one-time pad that is 1 megabyte in size, because this is what I want to send, I have to send a seed, which is actually far smaller. But this is still incredibly inconvenient. So this is where we say, hey, we are not going to use just the seed. We're not going to use just the encryption key. We're going to use something else. This is called the nonce or the initialization vector, depending on the exact terminology. And there are differences, but no one cares about them for this point. And the idea here goes like this. I generate the stream from the key and the nonce. And nonce stands for number only used once. So every time that I generate the key with a different nonce, I'm going to have a different output. So for each message that I'm sending, I'm using the same encryption key, but different nonce each time. Now, the really interesting thing about it, nonce doesn't have to be secured. The nonce can be made public. The nonce can be 1, 2, 3, 4, can be computed, whatever. The easiest way to say, okay, I'm sending you the message, and here is the nonce that was used here. If I don't have the key, knowing the nonce doesn't help me. So that drastically simplifies all of the above. And I'm happy about that, because now I have a key. I am able to send multiple messages. And we're good, almost. It turns out that there are two types of encryption models. One of them is the block and one of them is the stream. What we want is to take a block model and turn that into a stream model, so we can XOR with that. There are something called encryption modes. I'm not going to explain exactly what's going on. I want you to show you the electronic code book system. And the way that it works is that we have the key, and we take the key and the source data, and we encrypt them. And each time we encrypt, so in this case, I think that the size is 64 bytes. So now you can see this is an encrypted penguin. But because the same data encrypted multiple times would result in the same value, in this case, you can see the end result. This case, we haven't encrypted the data. We've actually just masked it, basically. So this is something that you have to be aware of. And this is part of the reasons why implementing your own security is so hard. because there are all sorts of modes and details that you need to consider. For that reasons, you want to use one of these two algorithms. This selects you the encryption algorithm, the key size, the mode, and everything else. This is also something that is called authenticated encryption. And let's talk about what is authenticated encryption. The whole idea is that I want to send you a message. How do we do that? I use AES, I use XChacha, and I generate a stream of cryptographically secure bits. I XOR that with the message, with the notes and everything, and I send it over to you. And you do the same. What happens if I change the value of the encrypted text? Keep that in there for a moment. We need that. So the whole idea with authenticated encryption is that we can ensure cryptographically that the data that I sent and the data that I got is the same. This encryption mode also have the notion of additional data. So this is some data that is not encrypted, that is set as plain text, that I'm also verifying. A good example of a server where I want to do that, I may want to send you the encrypted message, the nonce, and the position of this message in the stream of values that I'm sending. The position is not secret, but I want to also validate that. So this goes into authenticated encryption. We validate both that the data hasn't been changed, the additional data has been changed, and that gives us a lot of safety. Now, look at those two guys. The nonce for AES is 96 bits. The nonce for XChacha is 192. Why does it matter? Well, it matters because remember what is the one requirement from a nonce. The one requirement from a nonce is that it has to ensure no repetition. With 96 bits, you have the birthday problem. If you randomly generate the nonce, then once in 2 to the power 48 attempts, you're going to have the same value. And just let me give you what it means. So this is a big number. And in cryptography circles, this is considered to be really, really weak. So generating this randomly doesn't, you have to have some way of coordinating the value of the nonce so you wouldn't reuse that. Another problem is that the leakage of the nonce, you reuse the nonce just once and you're killing your entire security system. We'll talk about this more later. With 192 bits nonce, I have 2 to the power of 96, the birthday problem, and that's far more secure. So let's talk about what we want to use. For secret key encryption, AES or XChacha. Let's see how it works. I'm encrypting this thing. I'm getting this value. You can see this is using AES. This is the encrypted value. Now, look at this guy. This is set to 0. This is this value, the P. Because remember, what did I do? I took the plain text and I XOR that. If I know anything about the structure, I can now start changing the P to something else. And then I would be able to decrypt the value. And the 0 would be some other value. I need it to be 1 to be known as admin. I have 256 possibilities. I do it like that. And the reason this is important is because AES and Xchacha on their own don't provide me with authentication. And there have been many actual production errors because of this issue. This is why authenticated encryption is so important. This is the GSM and the Poly 1305 that you see here. Now, let's talk a little bit about nonce reuse. One time, you use the nonce with ASGCM. So you expose the XOR of the message. What does it mean? That means that I can now XOR the two messages together, the two encrypted values together. And now I see the XOR of the two plain texts. And that is sufficient for you to actually know that the message itself. It's relatively trivial to go from the system is encrypted, the value is encrypted to from the value is encrypted to I have XOR of the encrypted messages to I have the messages themselves. It also provides quite a lot of information about the secret key that you're using, which, as you can imagine, isn't fun to have at all. With Xchacha, you again expose the message, and it allows the attacker to force messages to pretend that this is a valid message that you sent. Remember, the whole idea of using authenticated encryption is to ensure that this is valid. So we'd be able to modify this value and forge the authentication token. There is an easy way to handle that. Never use a nonce. The way to do that is with 96 bits, you have to figure out some protocol to avoid doing that. A counter, maybe you say, oh, I'm using the current time, but I'm only sending one message a minute. But then you have to worry about what happens if time goes back because of daylight savings time or something like that. So this is actually quite hard. It's much easier to use a nonce that is big enough. 192 bits, you generate it using a random, cryptographically random, and you don't worry about it. So take that into account. Another option is to use an encryption algorithm that use nonce reuse resistance. And the way that it works, it's called SIV, synthetic initialization vector. And what's the idea here? Here's what we do. We hash, using the secret key, the message, additional data, and the nonce. And the output of this means that we have an actual nonce to use for the ASGCM or the Xchacha Poly 1305. What's the idea? The idea here is that if I'm reusing the nonce, then I'm unique on the message and additional data, which means that with nonce reuse resistance algorithms, if you reuse the nonce, then the only thing that the attacker can tell is that you sent an identical message. They can't tell anything more about that. You should still use random nonsense and whatever, but at least the catastrophic failure isn't here in the case that you missed. There is another issue here. It means that it costs slightly more. Why? Because you have to compute this from the get-go. It's even more important here because look what you have here. You have to have the whole message up front, which means that it's less suitable for streaming environments. And in general, my recommendation is to go with Xchacha or ASGCM, but go with Xchacha, generate the value randomly, and don't think about it. Now, another really interesting topic is passwords. I need to authenticate. If at all possible, avoid the need to authenticate. Use an authentication provider that will manage that for you. Now, if you do need to store passwords, if you need to authenticate using passwords, a few things to take into account. First of all, what do you store? Obviously, plain text password is right out. The stress that I have just thinking about that is enormous. It's to the point where I'm thinking that if you store plain text password, even for students' work in university, I'm seeing that and I'm like, big X on that. Even at that point, you should never do something like that. Typically, people then graduate to store in hash passwords, MD5, SHA, something like that. Never do that. Why is that? Because hashing, SHA 256, for example, is a hashing algorithm, a cryptographic hashing algorithm. On the face of it, it is meant to be used for that scenario, except that SHA is actually meant for one simple reason, to give you cryptographic security and be very fast, which means that software like Hashcat can do some ridiculous numbers, billions of hash attempts per second, which means that it's relatively easy. Oh, here, let's take the list of all passwords and all of the common passwords, and you just go and find, give me the million most common passwords and run that through Hashcat, and you have all of the hashes. There are environments such as rainbow tables, which can significantly optimize this even further. So from practical security perspective, hash passwords are identical to plaintext passwords. Now, there are algorithms specifically made for hashing passwords, Argon 2ID, for example. Now, what's the idea? The idea here is that Argon is meant for a very non-obvious problem. What we want is to ensure that this is not efficient. This is the case where our parameters and the algorithm was meant to be as inefficient as possible. And you can see that it is inefficient on multiple axes. So memory, number of iteration, number of threads, stuff like that. Why is that? Because the whole idea is to make it expensive to compute in hardware. So memory is expensive. So I'm going to use a lot of memory to compute the hashing function. I'm going to use a lot of iterations to increase the amount of time that this takes. And you can see some numbers about how long does this take. So 128 megabyte, 6 iteration over 8 threads would cost me almost a second, which means that brute force attempts to find my password are going to be really expensive. That's actually a downside of this because of my problem. Because now I can run a denial of service very easily. Just try to log into the system. And every time that I try to log into the system, I have to run this thing. And it's going to cost me 1 second of compute time and 128 megabytes. Well, what happens if I try to log in over 100 users all at once? Well, my server is probably going to go into the red line. That's expensive. So here's how we do that. We say this is the client, and the client wants to authenticate, and the client uses big details. So the client needs to compute the password hash using high secure defaults. And that takes time, but that takes time on the client. And then we get a seed from the server, and the server just generates some crypto numbers. It already have the previously hashed password. So it does this. Let's compute cheaply, using cheap mechanism, the password hash with the random seed. And this is cheap to run on the server side. On the client side, the client has to go through this, to compute this before it can do this. And because each time we send an authentication request, we send you a different cryptographic seed, you cannot do that in an offline manner, you cannot manage that. So you have to pay this cost quite often. And that gives you a good, this gives you a good security boundary for your needs. Now, so far what we talked about encryption, secret cryptography, and then we talked about password hashing. Let's talk about public key cryptography. What does it mean? It means that I have a public key and a private key. The public key, everyone knows. Private key, only I have. And it turns out that there are quite a few operations that you can make using this approach. You can sign something, which means that you generate a digital signature that proves that the owner of the private key has signed this particular value. You can encrypt the data. And this is funny because you can encrypt the data using the public key. So anyone can do that. You can decrypt the data, but only through the private key. And that's about it. Those are the three operations that you can make. Practically speaking, by the way, signing a digital signature with public key, with public-private keys means pretty much, okay, I'm going to encrypt using the private key and decrypt using the public key. But because the public key is public, then anyone can do that. But only the private key can encrypt. It's not actually how it works, but it's a good model to have in your head for that. Okay, so what do I want to use public key cryptography for? Why do I need that when I have secret keys? It solves a very simple problem. How do I generate a key for someone that I've never met? We use that to establish identity. So there is something called Diffie-Hellman key exchange, which is a mathematical way to generate a shared key between two parties without ever sending the actual key over the wire. This is easy to do. What isn't easy to do is how to prevent I'm generating part of the key, you generate part of the key, and someone in the middle replacing the key pieces along the way, the man in the middle issue. This is where public key cryptography comes into place because it allows me to establish identity. And it turns out that this is used every single time. If you will look at your browser right now, you will see a signal of a lock, which means that the communication from your browser to the server is encrypted. Which means this is done through HTTPS or TLS. So there is an XCHA key, AES-GCM key that is used to encrypt all of this data. But before we can generate the key, we need to know that the server that I'm talking to is actually the right server and not some nefarious person in the middle. So in order to do that, we have to know how do we trust the other side. There's a bunch of ways of doing that. The most common way in HTTPS is something called the public key infrastructure. On your system, you have a list of root certificates that you trust. Those are the public keys of people that you've chosen to trust. Now, you've probably never chosen to trust a root certificate. You rely on Microsoft, on Mozilla, on Google, Apple, to choose trustworthy root keys. And for example, a root key that you probably trust is the Let's Encrypt root key. That root key has signed an intermediary certificate, which eventually sign a certificate that was served to you by the browser. So the whole thing is a pile of recursive chain of trust. So someone hands me a certificate. I validate the certificate match my expectation. This is a certificate to the website that I'm actually trying to get to. This was signed by an intermediate that was signed by a root that I trust. That's one way of doing that. And this is by necessity. This is what we use in the public internet all the time, because there is no other way to coordinate. If you work in on your own environment, you may choose to explicitly say, okay, I'm going to trust this particular key. This is how SSH works, for example, where it says, oh, I trust those particular keys, and there is some other mechanism to distribute the key material. But the issue of key trust is really complicated. For public key security, there are two common algorithms, RSA and X2 blah, blah, blah. This one is based on this one is based on number factorization. So you start by finding two large primes, you multiply them together, and then you have your public key, and it's really hard to go the other way around. The problem with RSA is that you need to find two large primes. That can be an incredibly expensive operation. And there have been many issues with the primes that were selected. How do you find them? There are patterns that you may leak and stuff like that. Again, you have to do a lot of non-obvious stuff to do the right thing. With this one, the X25519, this is using elliptic curve cryptography. Again, I'm not going into the details of that, but the gist of that is that in order to generate a proper key for this algorithm, I need to generate a random number, which I already have to do for everything else. So this is far faster. It's much smaller and more efficient. So in general, I would recommend going with that if you have the ability to choose which encryption algorithm to use. Now, let's talk about key management. And key management is one of those really, really complex things that you have to deal with. Because in the end, all of cryptography sits on one simple rule. I want to be able to communicate safely. And at some point, I need to deal with keys. If I'm using public key cryptography, then I can use something like Diffie-Hellman to generate the key on the fly, which is great, except for one problem, that now I have the problem of how do I store the private key? So basically, that sucks. Key management is one of the more complex things that you have to do. If you're working with Windows, there is something called the Data Protection API, DPAPI. And that relies on the Windows cryptography mechanism that allows you to encrypt the details using the user's own password. It's slightly more complex than that, but that's the way it works. And this makes it really easy and simple to do. On Linux, there are something called rings or vaults or something like that that you may be able to use. That depends on the exact environment in which you're running. If you're running on GNOME, there is the GNOME ring. On Apple, there is also something similar. But in general, this is a tough problem. In the cloud, you have something called a vault, which is a way for you to manage secrets. On Kubernetes, you have the secrets management API. If you're running on a high secure system, you have hardware security models, and those are all ways for you to manage the keys. And that sucks because you have to deal with that. And it also means that you have to deal with how do I manage the key management? Eventually, someone needs to do that. And the easiest way of doing that is to just throw that to someone who is already secure. I have a password to log into my account. Presumably, I manage that securely. And if not, the door is already open. So the data protection API from Windows means that I can encrypt using the system manage secret is really compelling for me. If I'm using a hardware security model, such as a smart card or something like that, the security boundary is now at the smart card level. So I'm not going to touch on that. I'm just going to say that this is something that you have to consider, and this deals very clearly with how you manage your threat model, what are you trying to secure yourself from. But I want to talk about how do you manage the key once you gather. So first of all, key generation. Key generation, generate them through cryptographically secure random number generator. urandom is a great one. Why is that? Because keys are now have no patterns that you care about. You don't need to really think about it, none of that. With RSA, you have to generate the key on small systems that can be incredibly expensive. And again, people found patterns in the primes that are generated in RSA if you're not careful. So I like to use system where the key is just some random bytes, random bits. Once you have the key, we have to talk about hygiene. So the first thing that we need to understand is that we never want to use the same key for multiple purposes. What does it mean, multiple purposes? Remember that the key for this one and Exchacha are both just some random numbers. So I can do something like this. This is the key, and I can use this. And it will work. Both of them happen to use 256 bits keys. So it will actually work. And I would be happy because I have to manage one less thing. The problem here is that now a weakness in one system may expose me on other systems. So proper hygiene in cryptographic contexts mean that we never use a key. For that matter, I never want to use the key that I was given directly. Instead, I'm going to use something called a key derivation function. What's the idea with a key derivation function? It is a way for me to take some key and a context. The context may be derived key. Something like that. Now I generated from this key with this context a separate key. What key derivation gives me is a one-way function from the secure key that I have to the to some other key. If that key leaked, the root key is still secure. And in many cases, what you will do, you will say, oh, I'm going to generate, for example, a different key per day, per context in which I'm working on. So I'm working now on encrypted Word documents. Okay, great. I'm going to use a key for a derived key for that. And I'm going to now, I'm going to need a key to generate signatures for PDFs. So I'm going to generate a key from that, again, for the same purpose. And that gives me an additional level of security. And with that, I want to give some time for questions. You can throw them in the chat. The idea for this talk has been to give you better grasp of exactly what's going on when you actually use cryptography in your application. For the most part, I want you to think about this as theoretical knowledge only. And don't try to implement your own encryption. You should use something like libsodium or similar libraries that allows you to generate, that allows you to work with cryptographic primitives that have been validated. Their API was explicitly designed to make it hard for you to mess up. Like in this case, here we go. This API, it looks okay. It would pass probably code review, unless you understand encryption to a good level and says, hey, where is the authentication code for that? How do you do that? So this is something like libsodium bypass a lot of those arguments. Someone already made all of the good choices that you want. You still need to remember, hey, I have to deal with things like node generation. I have to maintain proper key hygiene. And I have to ensure that the key management portion of my system is working properly. And with that, thank you very much and have a great day.